Hi, this is a mathematical demonstration of average velocity, but everything we do here can be interpreted as average rate of change of a quantity f of x here, where x is a parameter, not necessarily time. But if f represent the position and t represent time, then the average rate of change of this position over time is the average velocity. So here's a demonstration. What it is shown here is this is a graph of that position function expanded over the time axis here, and the position of the particle, let's say, is actually over here. So the actual trajectory of the particle is linear, is moving just on this line, but as you expand this one over this time axis, we have this graph. So although its actual movement of the particle is one-dimensional like this, we're looking at the entire situation with the time axis in a two-dimensional situation. And in Newtonian space-time, we always assume the way this time increases is always steady. So to us, this time is always going by exactly the same rate. To everyone else who is observing or whatever, it's always going in a steady space. So that's our t, and you will see that t is increasing all the time at exactly the same rate to us. But on the other hand, the position will be different. So you can see from this demonstration, sometimes it's moving fast, sometimes it's moving slow. So that formula I've shown you before, 5t minus t cubed, is determining the position, and sometimes it's moving fast and sometimes slower. We're going to use this average velocity calculation to get a brief idea about the notion of a speed. So let me run this. So this vertical part is actually how it's moving, and never think that this is actually how the particle moves. This is just a kind of imaginary space we created with this time. So here it is. So you can see this particle is moving up and coming back down, and that's how much I got. So this algorithm repeats again. So as you can see at the beginning, it moves right here, is coming back down, is moving faster, and at the beginning faster, it's just slowing down, and it reaches the top and coming back down and getting faster and faster. It's quite similar to the motion if you throw a ball on the surface of the earth and it's going up and down like this. So I actually analyze it in this way. So these dots and on the graph, which is expanded over this time axis, showing that if I increase the time period by 0.1, and these are the positions. And then I actually plotted each of the position over here in the y-axis, so you can clearly see exact location of the particle after 0.1 second. It's a starting point, and 0.1 second later we're here, it's there, and 0.1 second later it's there. So these dots are indicating how much it moved after the fixed time interval 0.1 second. So after 0.1 second it moved this much, but if you look at this time period, after 0.1 second it only moved just a little bit. Okay, so I guess it moved faster here than this time period. So that's what we have observed up there. So if you look at the time 0.1 period, I kind of clearly give you an idea about how fast it's moving. So that's the idea of the average of velocity, and we're using this particular time interval 0.1, and there's nothing special about time 0.1. If you want a better a result, you can choose 100th second, and then you will have more points lined up, gives you a more accurate result about how fast these are moving at each of the point. So I visualize the quantity, the average rate. So for example, if I'm in this dot is 1, 2, 3, 4, so I guess, and this is where 0.4 second. So at the 0.4 second, we're over here, and the particle is located right that moment. So after a 0.1 second, it's over here. So if you calculated how much it moved, divided by its time interval, and that'll give you at that point here what the average rate of change is here at that point is. So I turn that notion here, the average speed, into a quantity. So quantity is represented here as the height of this thing. So when we sketch the value of the average velocity, and that means we turn that number into a height of this thing, height of this point here. So x is 0.4, and if you go up, it says, okay, it's a little more than 4. That's the average speed at that moment. So that's what this red line is indicating. So I got it here written down. This is the idea of the average speed. So what is the time period? Time period changed from A seconds to B seconds. So if you subtract it, so we're looking at this 0.1 second time period, just to get an idea. So this is the location of the position PA, and this is location of the position at time B. So if you subtract this position, you will see how much it moved during that time period B minus A. So this is amount of displacement of the particle and divided by time interval. That's exactly the idea of the speed. So that'll give you an average speed. So that's what it's sketched here. For example, if I look at this time period here, at that time period, if you go another 0.1 second, and if you look at it here, this is actual position. So that actually moved just this much over time 0.1 period. So you measure that carefully, divide it by time interval 0.1, and what it says is over there is it was moving faster than the 0.4 second before. So this one indicates I want you to look at the height of this each of that point. So at that, for example, at this point over there, and this height is suggesting this number here, like 3.5, for example, this is 4 and 2, suggesting that's 3.5 unit per second. That's how fast roughly it's moving during that time. So it's 1 second, it's moving a lot slower. So that's what this one is indicating. So we looked at this position function, and that's the first function given. And out of playing with this, dividing these pieces into tiny pieces like this, we created a new kind of quantity associated to it. Namely, we looked at the position at each point in here, we associated something called average speed. So let me summarize what we have just done and the way usually mathematicians summarize. So this is how they usually summarize. We're given a position function, and we looked at the motion. Then we can think about, okay, each of the position, we can see where it is, but we can think about this new notion. At each of the moment there, when the particle is going up or down, we can think of this average velocity at that moment if we allow this additional information, interval h. For example, that's a 0.1. So we have a new function. We created another function each moment that has associated with this time period t, and we associated another quantity. That's exactly a new idea of a function. So given function, we create a new function. So in our class, I used this example and as one of the example we went through as an idea of looking at a function. So position function is usually given by formula, so students should feel comfortable. Okay, here is a position function. I see the function given by formula, but this was an example that although you don't see the formula, we can think about a function in this abstract way. Whenever you see some quantity associated to the every variable, there is this functional relationship, whether you have a formula or not. So that was the main purpose of this example. But it also serves an important function to create and to study in the whole subject of calculus. The next idea is that what is that big deal about this time interval 0.1 second? Why don't we look at 0.1 thousandth second, and then this information of average velocity is really close to the information at that moment. So, for example, suppose this particle here has a built-in speedometer, and it recorded all the speed at each moment, and what would be the speed at that moment it's passing, going upward, something like that. Then if you look at a 1,000th second, you can see that in the period of 1,000th second, the velocity doesn't change that quickly. Therefore, this information we're calculating here is very, very close to the speedometer reading. So that is called instantaneous velocity as we take this time interval and smaller, and what is going to happen to the average velocity. So if you carry that calculation over and over, so we repeat this entire calculation over and over with a smaller time interval, and then your question is that what is going to happen to this average velocity function? It looks still a lot like this, but there's a subtle difference. It's going to change very tiny amount, but it'll be different. So I don't know if you've noticed it or not, and this looks like a position function. It looks a lot like a sine curve, right? So if you look at the sine curve, and the other one looks like cosine curve of something. So if you play this a game, not with a 5x minus x cubed, actually calculate with the computer with a sine x like that, sine t, then you will see this if you compare it, and it really is close to the cosine t. So that's the idea. So let me summarize this idea one more time. So it can be summarized again given a position function, and we've been looking at the average velocity over time interval, 10th seconds or a 1,000th second, and using the idea of a limit, you can push that result to h approaching 0. So if that limit exists, that's going to be our instantaneous velocity function. So given a function, what could be the instantaneous velocity at the time t? So that's the idea of a derivative. So what I was trying to say here is this procedure, given a function, getting a new function, and given a function, using more sophisticated idea and getting a new function. This idea of pulling a new function out of a given function is an operator. And in higher and higher mathematics, you will see more of this idea coming in, and understanding this operator and so-called operator algebra is this important idea in mathematics. So in advanced mathematics, you see this idea and try to understand algebra on this operator idea. It'll open up new door to and higher and higher mathematics, and I think it's important theme to pay attention in mathematics. So it's a beginning, so I want you to look at this situation in terms of this operator. So that's what's just explained here. Given function, we calculated lots of things, and we don't stop there, and we look at it as, okay, we actually created a new function, especially this one right here, instantaneous velocity, called if it is a rate of change, average rate of change problem. That's exactly what's called a derivative. Thanks.